it's great to be a visionary, but it's so much better to be a visionary working with a bunch of people who can build the future. So we like to say that we're engineering the future of space.
So we're here with Joel Sercel, the CEO of TransAstra. Joel, your visionary ideas for what our solar system and our future are going to look like are really inspirational. And I'd love to have, just your perspective on what is TransAstra, because I can try to describe it, but I feel like it's so broad, the ideas that you have.
So thank you so much for saying that. And by the way, I'm just delighted to be here and having you guys here in the lab where the magic happens. And I really appreciate you talking about the visionary ideas behind TransAstra, because it's very important, the vision of asteroid resources, larger than that, space resources, for the future of mankind, for the future of humanity, is deeply motivational to us, and it's the engine that drives us. But TransAstra is mostly not a visionary company. We're mostly a company of doers and builders who get stuff done. And
Right.
it's all about writing code that does amazing things, turning wrenches, building hardware, and making software happen. So what I would say is, it's great to be a visionary, but it's so much better to be a visionary working with a bunch of people who can build the future. So we like to say that we're engineering the future of space.
I like that.
Yeah,
I
me
like that
too.
a lot.
That's good.
Thank
So,
you.
what when you say engineering the future, what are the projects that you're working on right now? Like what kinds of things does TransAstra do?
Yeah, so what we do is, there's hundreds of things that you could work on in the space business. How do you prioritize and decide what to focus on? And it's that vision that helps us with the priority. So TransAstra is built on this vision of taking humanity into space so that we can harness the resources of the solar system for the betterment of humanity and the terrestrial environment. But then when you ask yourself, okay, so what am I going to do to enable that? We really break it down into four things. And we call them detect, move, capture, and process. And these are the four things that we as a species have to be a lot better at in a practical way in order to enable practical asteroid mining. So detect is our telescope system, because we have to be much better at finding faint moving objects in space. And that's where our connection with Celestron comes from. That's where we use telescopes like that, but integrated into very sophisticated systems to do that. It's for prospecting asteroids in the long term, but today we're doing work for the government, including Space Force and other agencies, to find faint moving objects in space. So it's detect, Sutter telescopes. Our telescope systems are named after Sutter's Mill, which is a place in California where in the 1840s they discovered gold. And we think that these telescopes are going to help us discover enough resources in space to lead to a gold rush to the solar system. So it's detect. The second one is move. That we need to get better at moving around in space. We're really grateful that companies like SpaceX, Blue Origin, Stoke, ABL, these wonderful rocket companies are building relativity, are building much better rockets to get us into space far less expensively and far more safely. But once you get into space, once you get into low Earth orbit where the rockets drop you off, you're only halfway to where you need to go. Whether it's geostationary orbit for communication satellites, or the asteroids for asteroid resources, or the moon. So we need better ways to get around in space. So we have invented propulsion systems that are vastly more practical than today's rockets, that use the power of the sun and can use virtually anything as propellant instead of dangerous and toxic fuels that you need to get into orbit. So there's detect, there's move. Then there's capture. So the third area that we're working in is called capture, because eventually when we're mining asteroids, you cannot land on an asteroid. By the way, here's a way you can tell if someone knows anything about asteroid mining. They propose asteroid mining and they show you a picture and it shows a spacecraft landing on an asteroid. So
Mhm.
Right.
technically and scientifically, we know that asteroids have gravity. But when you actually measure the amount of gravity they have, if you were there in a spacesuit, you wouldn't notice it. So instead of landing on an asteroid, our plan is to capture asteroids in what we call capture bags. And we've invented the fly trap capture bag, which one Time magazine was noted it in its Invention of the Year awards last year. We have millions of dollars of contracts with Space Force, NASA, and other organizations to build capture bags, which we'll eventually use for asteroid mining. But today we're working on very practical problems associated with orbital debris cleanup in space. And then the last area, process, is materials processing.
So if you're doing this first capturing, space junk,
Yeah.
what is the end result of it? Are you deorbiting it? Is it potentially useful? Because I was thinking about this earlier today. If it's already in orbit, the vast majority of the work's been done. And to throw away all of the resources of a spacecraft that is rich in all of the things you need to make a new spacecraft, it seems like recycling it might be a better option than a deorbit. Is
Yeah.
that something that's being considered?
Yeah, absolutely. In fact, before we started to get in the game of orbital debris cleanup, the assumption was generally that there's big pieces of orbital debris that are very dangerous up there that need to be cleaned up. And the assumption was if there's a big piece of orbital debris, you send a space mission to it to somehow precision rendezvous with it, grapple with it using expensive robotic arms, and then you deorbit it.
Right.
And
Yeah.
the issue here is that the really dangerous orbital debris is in orbits that it takes a fair amount of delta V, a fair amount of rocket propellant to deorbit them. So we
Mhm.
took a look at that in the light of the capture bag, and we realized totally, Dave, exactly as you're saying, that's a lot of really valuable resource up there, metals and that sort of thing.
Right. Already in its enriched form.
And we realized that instead of doing it the way other people have been talking about it, we use our capture bags, which are much more cost effective for capturing the debris because you don't have to do precision docking and you don't have to have complex mechatronic systems to grapple with or dock with something.
Yeah, it seems
Without
overcomplicated that way,
It's
right?
overcomplicated, right?
Absolutely.
Whereas the capture bag is a much simpler approach.
I'm imagining like the Apple dongles that you have to get for the computers. Like you'd have to get a docking dongle for this one, and
Exactly.
you'd have all
Exactly.
sorts of stuff where you'd have no innovation in the docking mechanisms, and that wouldn't be good either.
Exactly. So instead, what we do with our capture bags is we fly up to and capture the device in a bag, and it can still have some residual nutation and rotation relative to the very crude, more like a berthing than a docking procedure. That's not technically the right word, but you get what I'm talking about. Um, then, but we have patents on how we can capture one piece, another piece, another piece, another piece,
Hmm.
all in an orbital plane. So think of it as Pac-Man flying through an orbital plane. The debris
Nice.
tends to collect in orbital planes, statistically, when you look at it. And so there's not much rocket propellant required to go as you're going along collecting the debris in a plane. It's a little bit of this and a little bit of that. And then, and because of the capture bag, we can do several pieces of debris on a single mission. And then instead of spending all the delta V, all the rocket propellant to deorbit it, throwing that valuable resource away. And by the way, people are now starting to get very concerned about the quantity of debris that's starting to build up in low Earth orbit. There's some concerns about damaging the upper atmosphere here. And there's some pretty
Hmm.
toxic chemicals in some of these things.
Hmm.
So instead, what we'll do is we'll bring it to an orbital processing depot.
Yep.
And there we'll use our material processing technology to separate out the different metals into raw materials, because other companies are very rapidly developing the technologies to make practical spacecraft components, space station components, usable structures in space out of metals that we can process out of these orbital debris.
Right.
So, so it's kind of interesting to think about. The orbital debris problem is a small version of the asteroid problem. I like to say that the asteroids are the debris that are left over from the early formation of the solar system. Yeah. So the way that I think you have a pretty literate listener viewer base. So most of your viewers know that the solar system was formed from a disk of gas and dust that accumulated due to gravity and formed a flat disk, and then the dust and gas aggregated into the planets, but not. And as it was aggregating, there used to be a lot more asteroids than there are now. They aggregated and formed the planets, but the leftover asteroids that are still being collected by the planets or spiraling into the sun are the roughly billion asteroids that populate the solar system today. And so I think of them as the debris left over from the construction project that was the building of the solar system. And so we're going to go out and harness that debris, for humanity. And the four problems that you need to solve for doing that are: you got to find them, that's detect; you got to go to and from them, you got to move; you got to capture them, you got to process that material. It's the same four problems that you need to solve for orbital debris. So orbital debris is a very early, easy version of asteroids that we are moving into very quickly as a commercial business for both government, U.S. government, international partners, and private companies in the U.S.
You mentioned Blue Origin, and I know that I've heard some things from Jeff Bezos that I watched some of your content on YouTube, and so very similar ideas and very large habitats in the very far future. What are your thoughts on how we progress? Like, what does success look like for TransAstra?
Success for TransAstra looks like Thursday. I feel incredibly good about how the company's doing. We're still small and seed stage, but we're growing at 50 to 100% a year this year. I mean, already in the first quarter of this year, we've won half the contract value that we did for the whole of last year. So we could easily double our revenue from last year. But of course, we don't want to stay small forever. So success in the short term is, we've had tremendous success already. For example, with our network of telescopes, and I hope your viewers will get to see what those look like. We operate compound telescopes in California, Arizona, and Australia, and the Space Force right now is paying us to build 2 more, and then we're very optimistic that we'll have contracts to do others. Our telescopes right now today are the most sensitive commercial sensors for finding things in cislunar space. To me, that's success. But a bigger success is building a global network of ground-based telescopes, and then working with our partners like Celestron. We're planning on space qualifying those telescopes and putting them into space where you can see things that you can't see from the Earth so well, and using them to prospect the asteroids. So that's one form of success. Another form of success is to be the world's preeminent trash collector in space. We're in the trash collecting and recycling business. And
I'm thinking about Wall-E, the cartoon with the trash collecting robots.
Yeah. So the world that Wall-E was in was a Earth where they didn't have proper trash collection and recycling on the surface. But we don't want the orbital debris to build up to be, like the rings of Saturn around the Earth, so that you can't get around safely. Already, orbital debris is one of the chief safety concerns for traveling in low Earth orbit. And, you're right. Jeff Bezos talks about a future where humanity lives in space in huge habitats in space. I think I have tremendous respect for him and his accomplishments and his directions, and I love his vision. The one thing I would like to see from him is more alacrity and urgency to get it done. So Actually,
Right.
with what's happening in manufacturing technology, robotics, and AI right now, there's no reason why that has to be a distant future vision. That can be something that can happen faster than we can possibly believe. But to enable that, we've got to be harnessing the resources of space, the resources that are on the surface of the moon, the resources of the asteroids, even the resources of the Martian moon.
That's just such a cool vision to think about the future in that way. And we've been talking a bit right now about satellites of the Earth,
Mhm.
right? And how we're going to clean up the ones that we've put up there. What I want to do, which we didn't get to in the beginning here, but what I want to do is I have a trivia segment for us right now.
Does Dave stand a chance against Joel at our next round of last minute trivia? Find out after this short break.
Introducing Celestron Origin, stargazing and astroimaging redefined. Origin is completely autonomous. Simply choose a target in the app. Origin captures it with ultra-fast RASA optics, perfects it with AI imaging processing, and delivers it to your device. The results are better than what you'd see in a much larger telescope under much darker skies. Experience and share the night sky like never before. Learn more at celestron.com/origin.
I've got 3 questions. Okay. The first question, let's do this. This should be an easy one, I think, in my opinion. First question is, what was the first artificial satellite of Earth, and what year was it launched?
Well, there's some dispute about that,
Okay.
depending on your definition of an artificial satellite. But of course, everyone says Sputnik, right?
I know where you're going with this.
57 was it? I don't know the year.
You got it. It was 1957.
But there is a story that the first thing that humanity sent into space was a manhole cover
Yes,
from a nuclear test in New Mexico.
that's what I've heard as well.
There is a story that the manhole cover, basically, they used to do subterranean tests of nuclear devices, and they had a deep tunnel to a subterranean test of a nuclear device with a manhole cover on the top of it. And someone allegedly calculated that that manhole cover was launched into space at a delta V of about 70 kilometers per second. Now, I spent a fair amount of time in my youth thinking about working on pulse propulsion, nuclear pulse propulsion. One of my teachers was a guy named Freeman Dyson, who was a mentor of mine for decades, who was the kind of the chief scientist of the Orion project, which was the nuclear pulse propulsion project. And I've heard rumors that that test was part of the inspiration for the Orion project. So, but anyway, not to derail the conversation.
No, that is perfect. I'm gonna give you triple points for that and subtract points on my end. That was fantastic.
But I'm not going to say that I believe that story, but I'm saying that there is that story.
There's a technical possibility there.
I wonder what year that would have been.
It would have been
57.
It would have been relatively early in the nuclear test program, so it could have been, decades before Sputnik.
Okay. Yeah. All right. Question number 2.
Okay.
And I think you'll know this, or at least have a better idea than I did when I looked this up. How many satellites are currently in orbit around the Earth? In other words, what is your future trash pickup look like?
Yeah. So it depends on what day it is. As recently as a few years ago, the total number of satellites, before the current wave that had been launched into space since Sputnik was only a few thousand. I think it was something like 3,500. And there have been approvals written by governments for network RF frequency allocations for tens of thousands of satellites to be launched within the next single-digit number of years.
Oh, wow. I mean, I knew Starlink was going up there, and they're putting tons of satellites up there, but there's even more than that.
There's more than that. Starlink is the first, and I think it's the first mega constellation that's been deployed, and I think I don't think it's premature to say Starlink is going to be or is a commercial success. And that is a huge game changer.
I know I want one. It's just the convenience of being able to travel and have high-speed internet. It's phenomenal.
We use Starlink every day at TransAstra. We don't have a Starlink here in this laboratory for various different reasons, but we have 2 remote employees who, I spend hours Zooming with every day on Starlink. And let me tell you, like, one of them is in near Sonoyta, Arizona, where we operate a telescope system. Where the sky is really clear in the mountains near the Arizona-Mexican border. And there's just no good internet down there. And it was just a real pain for him to use the internet until he got Starlink. And Starlink's amazing.
So what kind of satellite is Dave Matthews talking about in the song? Is it A, Sputnik, B, Hubble, C, the moon, a natural satellite, or D, who knows, it's art. It's up to the interpretation of the listener. Please stop overanalyzing lyrics.
Well, I have to go with D.
There you go. 10 points for you, and you have now won. In fact,
I think he
did look it
telegraphed
up
that with his body language.
Yeah, I mean, here's the thing. I actually did look at the lyrics, and it is actually pretty fairly literally about a satellite. If you actually look them up, it's actually pretty good. But of course, they're vague enough so you can put your own meanings in there. And there was an interview with Dave Matthews, and he said he doesn't even really know what it's about, but it might be something about death and the loss of his father or something. So, but yeah, it is pretty much a satellite. Tell us a little bit about how you use telescopes for your near-Earth asteroid finding. In fact, I was looking at one of your videos, and it said that there are thousands of near-Earth asteroids about the size of a house, and that
there's more than that.
me.
There's more than that.
So, like, how do you use telescopes? Like, how are you working with that to find the asteroids?
Sure. So let's be clear. There's way more than thousands of asteroids the size of a house. Now, a lot of times people who are technically informed who hear me say that say, wait a minute. I saw, NASA presentation where the scientists got up and said, there's 30,000 NEOs or 40,000 NEOs, something like that. But that is the number of known asteroids.
Yeah, confirmations.
And the vast majority of the known asteroids are really big.
Right.
And, NASA has been doing a valiant job to find the asteroids that could impact the Earth and, cause damage and destruction and so on. And so they've been looking for the big ones, like kilometer size or football field size asteroids. And those are pretty easy to see with conventional telescopes. And so, we know where 90% of those are. But asteroids follow a size versus frequency distribution, like so many things in nature. That's a power law. And the exponent in the power law, so I'm geeking out a little bit here, but the exponent in the power law is about 2.7, most people think. So what that means is, let's say you have 100 1-kilometer asteroids. When you go down to 100-meter asteroid, there's going to be 500 times more of those. And then when you go from 100-meter asteroids to 10-meter asteroids, there's going to be 500 times more of those. So what's 500 times 500? That's 10,000, 250,000 times more 10-meter asteroids than 1-kilometer asteroids. So there are a lot of asteroids in the small size range. So actually the estimates are anywhere from 100 million to 1 billion total asteroids, when you include ones that are down to the size that we really want to mine for asteroid mining. And so at TransAstra and our partners, speaking particularly of my good friend, Professor Robert Jedicke, who's just became emeritus at the University of Hawaii. We have Rob was kind enough to put me as a co-author on a paper that I helped a little bit with in this area. We have what I think is the best model of the statistical distribution of asteroid resources that are economically viable in the solar system.
Okay.
So when I say that we're very confident that there are thousands of asteroids the size of a house, I'm talking about a very particular population of asteroids, which is a tiny fraction of the hundreds of millions of asteroids in the solar system, that are in very, very Earth-like orbits around the sun. That is, the sun goes around and the Earth goes around the sun in an orbit that's 1 AU, 1 astronomical unit, like 1.5 times 10 to the 8th kilometers from the sun, nearly circular, by definition, no inclination, and very small eccentricity. So asteroids that are in highly Earth-like orbits, just like that around the sun, but spread all the way around the sun, those ones are a magical kind of asteroid to us, because it takes very, very little rocket propellant, delta V, for us to go out to them and go mine the materials and bring it back. So those are
they're
the
moving
first
with
ones.
us, essentially, right? Like we're in the same orbit.
We're in the same orbit. They're co-orbiting with the Earth around the sun.
Right.
There is a slight population deficit exactly at the Earth's orbit, because the Earth kind of sweeps them out. But then there's an accumulation a little bit around that. But our model suggests that about 5,000 of them, of which all of science knows about, I think at last check, 176. And of those, like 10 were of materials that we would be interested in. So not enough for the gold rush to space. So those are the ones that we need to focus on. The problem is, typical astronomical telescopes are not very good at finding them, because anyone who knows about photography knows, if I want to take a picture of something very, very faint, the way that I do it is I lock my camera onto it and I take a very long exposure. All right, so that works great if I'm taking a picture of the night sky and I want to see a faint galaxy or faint stars. I do sidereal pointing, which means I point at the background stars. I take a long exposure. So a backyard astronomer with a Celestron telescope with a nice Sony focal plane can take a 15-minute exposure of a very faint galaxy, and it's just amazing, right? The problem is the asteroids are moving. And while you're taking that long exposure, they move between pixels. So they don't get any benefit at all from the long exposure. So what do you do with that? Well, you say, well, if I know where the asteroid is, instead of tracking on the background stars, I can track on the asteroid. Yeah, but we don't want to track on asteroids that we know. We want to find unknown asteroids.
New ones, yep.
Right.
New ones. So there's a process called synthetic tracking, or shift and add, or match filter tracking. It's got a lot of names, but it's basically the same thing. It's been around for decades, where instead of taking a long exposure, take a whole series of short exposures. And then you guess, okay, if there's an asteroid moving in this trajectory, I'm going to take a series of exposures. I'm going to take this exposure, then I'm going to add it up to one that's shifted over one, and add it up to one that's shifted over, shifted over, shifted over. And if I happen to guess just right, so the asteroid is always then on the same pixel, and I add them up in the computer, it's as though I took a long exposure of that asteroid. You say, all right, no problem. Well, it turns out that scientists have been doing that actually for a couple of decades. And there have been thousands of main belt asteroids found that way. What they do is they take a big telescope with a nice focal plane. They do sidereal tracking. Then they take the stack of images. They put the terabytes of data onto a big hard disk somewhere. They feed it into a cloud processor. It used to be a supercomputer. And months later, they get all the tracks of all the asteroids. Well, the problem is with the little ones, if you wait months later, you'll never find it again. And because it's too computationally intensive. So even the focal planes that are very affordable that we put on our little telescopes are 60 megapixels plus. And we're taking 5-second exposures, adding those 5-second exposures up for 5 or 10 minutes. And if you look at the number of computations required to take every possible vector of every possible asteroid in that space, is untenable.
Right.
And so what people do is then people say, oh, shift and add or match filter tracking, that's nothing. We do that. And you go, well, but what you have to do is you have to do it real time. So,
Yeah.
So over here, there's a computer cabinet with our computers, with our test bed for our computers. So we have racks of computers tied to our telescopes that do those calculations real time, because we collect terabytes of data off our focal planes every night. There's no way we could download them to the cloud or upload them to the cloud, then do cloud processing on them. We have to process them at the edge. So we started processing it at the edge, which you can just do with modern GPUs, the kinds that high-end gamers use. And so we got rack-mounted computers with high-end gaming GPUs. And then we realized, well, what we really want to do is we want to put these in space. And space processors are much weaker than ground-based processors because you just don't have the power and cooling in space. And you got radiation concerns. So what could we do to make it much more efficient to do these calculations? Now, people have been thinking about it for decades, how to make it more efficient. And there's really no good, clever mathematical way to make it more efficient. It's an irreducible, to the most part, it's a mathematically irreducible problem, and beyond the normal efficiencies that you use. Then we realized, it's the way that we handle the images and the way we take the pictures. And so we fundamentally invented new ways of organizing the images and ways that we task the telescope that are optimized for finding these moving objects. And we can reduce the computation requirements by many orders of magnitude, such that we can easily run these computations on a little computer that'll fit in a CubeSat, a spacecraft, the size of a shoebox.
Mm-hmm.
And that's very exciting. And it makes it very affordable for us to. So the Space Force is paying us to build an observatory system that we call TKO, Turnkey Observatory, that has 18 of these telescopes, each with a 100 megapixel focal plane. And
Wow.
we can real-time process those on very affordable computers here on the ground.
18 scopes? 18?
Yes. Yeah. So we should show you what our 18 scope TKO system looks like. And we want to put those all over the Earth. So it's 18 of these very cost-effective but nicely made, professionally made Celestron telescopes that, you could buy at a camera store. They've got an 11-inch aperture, very nice engineering. They do the trick. You have to know how to use them. You have to know how to, correct for thermal drift and all that kind of stuff. We do a lot of really precision engineering here to make all that happen autonomously. But we can take 18 scopes, and I think we can show you guys pictures of our 6-scope system.
Now, are these 18 telescopes all pointing in exactly the same location? Are they offset from one another? Or are they overlapped?
All of the above. So we have a lot of really good mechatronics engineering here at TransAstra. I wasn't planning on showing this on camera, but let me show you this.
All right.
So this is a 3D print of the original prototype concept that we had about a year ago. The design has changed since then. So this is a children's toy size model of a 20-foot shipping container that's been modified to be an observatory with 18 telescopes in it. Now let's see what happens. It gets shipped as per any shipping container. And then once it gets to the target, let's see if I can grab one of these out. I'll probably drop it and it'll break and people kill me, but that's okay. I'm the CEO. So that's what the 18 telescopes look like in the shipping container.
Oh, wow.
And for scale, each one of those white things with a red dot on it is like that telescope right there.
Okay.
For scale.
That's a RASA scope, right?
It's a RASA 11. It's a Celestron RASA 11. These telescopes can do RA and deck adjustment here with the normal precision of any astronomical instrument. But they also have the ability to either co-bore sight, so you can put all 6 on top of each other.
Okay.
And then you can put all 3 sets of 6 on top of each other. So you have 18 telescopes, all core bore sighted. So if you want to go deep. Or we also have actuators so that you can orient them so they form a line in the sky. Then you can sweep
Oh,
that line across the sky for survey mode. And you can't go as deep. You can't see as faint an object, but it's a very powerful system.
and you can actuate them on demand.
Yes, you can actuate them on demand. So we have a very sophisticated telescope operating system that controls our global telescope network called MIDAS. And MIDAS runs on our data acquisition and control system, which is called DAC-Astra, which is a new commercial product that we're developing, which is DAQ stands for data acquisition and control. And we build the DAC-Astra system into everything that we do here. And it allows us to do precision mechatronics on everything that we build. And so you can sit in your office and control these telescopes anywhere in the world. And if all of a sudden we find a target, or if all of a sudden we get a phone call from the Space Force, hey, there's a target at this RAN deck that we suspect, we need you to go look deep at it, we can point all 18 telescopes together at it and go deep if it's faint. But even a single RASA with our software on it can see a CubeSat at 300,000 kilometers. So recently, the Space Force asked us to take a look at a Chinese spacecraft that was transiting to the moon. And at a distance of 300,000 kilometers, we saw a CubeSat separate from it, and we reported that to the Space Force. And they go,
Wow.
wow, that's really
Wow.
good. No other commercial company that we know can do that. So
Now with the high megapixel, I realize you do get a fairly digital zoom, if you will, on an object. Is there any benefit to having like a higher focal length telescope in this array that you can, then train that higher magnification on, or is it just it's too dim
The-
to be able to really
No. Look, the reason that we have wide field of view scopes is because we're looking for things. You don't look for
Right.
something through a soda straw. Most astronomical telescopes are very slow optics. We have fast optics, which means wide field of view. But narrow field of view, like the Hubble Space Telescope, where you're looking through a soda straw, that's great for some things, but it's not great for finding tiny objects in space.
I guess my question is more within the array. You'd have like a lot of wide field scopes, but to have like one main scope that then could be instantly able to zoom in on it, or is it just a communication with a real, large observatory that could do that?
Yeah, look, once you find
better?
it and you get the RAN deck, there's lots of telescopes
Report
that can. And by the way, if you know where something is, anyone can track a CubeSat in cislunar space. Anyone can do that who's got minimal competence. Well, you have to be a fully competent professional telescope operator to do it, but anyone who's got the competence of a journeyman can do it. And we report our findings to the different governments of it, the government agencies that are looking for stuff that's important to find. But the
Right.
problem with really narrow field for this is that they're moving pretty fast, and especially for cislunar topics, for cislunar objects, but also for objects in heliocentric space. Orbit propagation is a real black art. When we find something, we get what are called tracks and tracklets, a series of RAs and decks that tell where they are. Then there's a non-trivial mathematical process that you have to go through to convert that track. The track is a set of tracklets. Tracklet is a small set of observations. There's a non-trivial mathematical process that you have to go through to figure out, just because I saw something moving like this in space, was it something really close, moving slow? Something really far, moving fast? And you have to know something about astrodynamics and dynamics.
And what's that z-axis? Is it directly going, towards you, away from you? Is it on an angle?
It could be gumping like this. And so it turns out that you have to mathematically fit that to a series. You have to do a search algorithm. It's mathematically fitting the curved arc that you saw to all the different possible trajectories to get it.
Got it.
And then in order to get an accurate trajectory, you need many tracks that are far apart. The problem with astronomical telescopes, and the reason the vast majority of small objects are lost, is they get an initial tracklet. By the time someone looks at it again, the trajectory is not well known enough that a narrow fielded telescope can see it. Even if you think you know it pretty well, if you look at it with a narrow field of view scope, you're liable to not see it.
Dave and Rob check out the RASA 11 in this month's In Focus Product Spotlight.
The kind of cool thing about the RASA design is because it's collecting light so fast, you actually don't need to be guiding always. You can get away with normal sidereal tracking in most cases.
Well, Dave, thanks for bringing me out here. You brought me out here to check out this RASA scope. Now, I'm no expert in the RASA scopes, but from what I know, from what I've read, is that this is the type of scope that you want to get if you just want to do astrophotography, right?
That's right. This is a telescope that you actually cannot look through. It only can be looked through by a camera, and the place where the camera goes is kind of different in that it's up at the very front in the prime focus position, as opposed to behind the telescope's mirror at the back, like you would normally see on like a Schmidt-Cassegrain. Now this is the Rowe Ackerman Schmidt Astrograph. Which
That's a mouthful.
it is. The RASA. And the kind of crazy thing about this is just how fast it is. It's an f2.2 telescope, which
So that means like most, like an SCT. I have a Schmidt-Cassegrain. It's like a 10 or 11 inch one. And that is an f10, right? And this is an f2.2. So what does that mean?
So basically every time you change the F ratio by basically doubling the amount of light. Now, because we've gone very many F ratios, it's extremely fast when it comes to imaging.
And that's because the focal length is that much shorter. Is
That's
that
right.
So it's about the same size aperture, but the focal length is shorter, so you can get more light.
That's right. So this is only 620 millimeters of focal length.
Okay.
An equivalently sized Schmidt-Cassegrain is at about 2,800 millimeters of focal length. The way you calculate the F ratio is you take the focal length of the telescope divided by the aperture of the telescope. So for this telescope, you would take the focal length of 620 millimeters and divide it by the 279 millimeters of the aperture.
Okay, so that gets you the 2.2.
That gets you the 2.2.
So in other words, compared to my SCT of a similar size, less exposure in order to get the same amount of light and picture that I want, right?
Yep, and so, you know, for us here in Pennsylvania, we don't get a whole lot of cloudless nights.
Yes.
And so that time that you have is at a premium. And when you have a RASA telescope, which does come in 3 different sizes for 3 different budgets, right? It comes in the 8-inch, this is the 11-inch, and then there's a 36-centimeter version, which is approximately 14 inches.
Right, okay.
And with each of those, you get from the 8-inch to the 11-inch, you're getting about double the amount of light gathering power. And that's just because of the aperture. And that big step, you know, also gets you that faster image.
Okay. So then what about the focusing? I hear there's something special about how you focus on this thing.
Right, this is the V2 version, and it has the ultra stable focus system, which basically means that the mirror in the back here is kept very, very much in place when the telescope is in motion. So if you're looking at one place in the sky, you move to a different place in the sky, the position of the mirror stays the same. Now, if you remember in like a Schmidt-Cassegrain, the mirror is actually what is moving to achieve focus.
Okay.
The same thing is happening here in the RASA telescope. The mirror is in motion to get focus, but the ultra-stable focus system allows it to stay in place in a very, very rock-solid way.
In this one, the light's coming in, bouncing off the mirror, going through some optics here, bouncing off the mirror, and going up to the camera that's up there.
Correct.
Right? Now, can that take any DSLR or any type of camera or what?
It has a T adapter, which can be adapted to your DSLR camera, a mirrorless camera, and then there's a separate adapter that is a 48 millimeter threaded adapter for your astronomical cameras as well. So yes, you could have all of the different types of camera, and here we have your Canon full frame, which it can handle that, which is pretty incredible that it can handle a full frame camera. Not all telescopes can do that. This has a very large imaging circle to allow for the cameras up to the very large format sensors to be able to be adapted onto this.
And the camera's not actually going to be blocking that much of the light, right? Because
Right.
it already has the sensor up there that's blocking some of it. And the camera just adds like a little bit. It's not actually going to come out in the pictures, right?
Right, and even in a Schmidt-Cassegrain, you would have that central obstruction as well, and Newtonian's the same way.
So let's say I actually go out and get something like this.
Jesus. Sorry about the chickens. If you're hearing chickens in the background, we're out at the farm right now.
Yeah.
Getting nice dark skies, right? You gotta sacrifice some things.
So let's say we go out and let's say I buy this thing. What kind of mount do I want to put it on, or what kind of mount can I put it on?
So of course, with the 11-inch, you are gonna need a pretty substantial mount to place this on. But the kind of cool thing about the RASA design is because it's collecting light so fast, you actually don't need to be guiding always. You can get away with normal sidereal tracking in most cases, and that's nice because you can, have a little bit less mount as a result. Now, the weight capacity of the mount needs to be correct for the scope you have. The bigger the scope, of course, the larger the telescope mount. But the precision of that guide is not required as much as it would be in a normal telescope, especially with an f10 telescope like a Schmidt-Cassegrain.
Now you're saying that this has a very wide field of view. So is this something that you don't want to use for really small stuff, or can you still use it for that really small stuff?
Well, because you're collecting so much light, the kind of amazing thing is you can put very high megapixel cameras on the telescope and still collect enough light even though those pixels are very small. And so you effectively can digitally zoom in. So you're right, there are better options for very small objects, but you can actually get a pretty impressive digital zoom cropping in even with this very wide field. Maybe if we have a chance, we could start to do some of the asteroid searching for ourselves, right? We've got a pretty capable telescope here, and maybe we can discuss trying to get some of the software capable to start looking for asteroids on our own.
That would be quite the trek. Well, yeah, this is the first time I've actually seen RASA, and it's a really cool, upgrade from an SCT, and I'm actually looking forward to hanging out with you a bit and taking some pictures. I'm looking to see what I can get.
Yeah, now that we'll have some time this summer, hopefully we have some nice clear skies, and out here on the farm we have some really dark skies. We can see some Milky Way, and even though we can see Milky Way and it is that dark, I cannot even get away with a 30-second exposure because it is so overexposed.
Really?
Which is incredible.
Nice. That's fantastic. So it's going to make it a really good scope for these guys then.
And we'll have to come back and show you guys what an image looks like through this telescope in the months to come.
Yeah, looking forward to it. We've got 2 last questions of trivia. Then we'll get into the asteroid mining and then how your company works in the future and that sort of thing. So
Nice.
I've got one question here. The first one is the total mass of all of the asteroids in the main asteroid belt combined is less than the mass of, and I'll give you 4 options here. Is it A, Jupiter, B, Earth, C, Earth's moon, or D, Mars's moons put together? So again, the total mass of all the asteroids in the main asteroid belt combined is less than the mass of Jupiter, Earth, the moon, or Mars's moons.
So it's about 4% of the mass of Earth's moon.
That is correct. That's what I've got as well.
I have no chance.
Now, I'm sorry. Was I supposed to let Dave answer?
No,
No,
Okay.
you're number
no,
one.
you always get to go first because you're the guest.
And then my sense is that Phobos and Deimos are probably a small fraction of that mass. But
Yeah.
you happen to know?
No, I'd have to actually go back and double check that. But yeah, I have that it's less than Earth's moon, which
It's
is,
4%. It's roughly 4% of the mass of Earth's moon. By the way, I get asked that a lot.
Oh,
That's
really?
why I knew the answer. And the reason is that people go, they say, what are you talking about? So I talk about, so there's an interesting dialogue that comes out of this, which is I say, By the way, when I was a young man, we thought it was more like 12% of the mass of Earth's moon. So we didn't know the mass of the asteroids. There's bigger air bars. The air bars are a lot smaller now than they used to be.
Right.
And Gerard O'Neill, who was the guy who really came up with and put science and engineering behind the concept of large settlements in space, had calculated then that you could build worlds in space with 5 meters of radiation shielding with a total land area of 3,000 times that of the Earth. And in 2013, I did a Keck Institute of Space something, KISS, study at Caltech with JPL and Caltech on asteroid mining. And I updated that calculation to suggest that it's not 3,000 times the Earth surface, it's 1,000 times. So it's enough resources to support a population 1,000 times greater than the population of the Earth, or in round numbers, close to 1 trillion people. And people say, well, how can that be? Because you're only talking about a mass that's 3% of the mass of the moon. Why would we need to move off the Earth for resources?
Yeah.
Well, the answer is interesting. And it's a couple of things. The Earth is a geologically differentiated target. So we use the term ore in mining on the Earth to mean you found something that has something useful in it. Most ores on the Earth are in veins. And what these veins are is these are veins of leftover material from the formation of the Earth, because all of the precious metals went to the center of the core of the Earth because it was geologically differentiated in its formation. And most of the stuff on the crust is not really what you want for a lot of different things. Whereas if you go to a metal-rich asteroid on the in the asteroids, that whole thing is an ore body. And
it was the core parts of the not totally formed planet, right?
Yeah. And then the other thing is, most of the mass in places like the Earth and the Moon is useless because you can't dig that deep. And then the really big thing is, the reason to go into space is to have an unlimited horizon. Captain Kirk's The Final Frontier, so humanity can expand and grow. And as soon as you're in a gravity well, you're limited there. And if you're in the Earth's gravity well, everything you do affects every other living thing on the Earth. And, for example, we need to learn to process energy in order for humanity to continue to grow exponentially as a species, which, by the way, whether we like it or not, if we're going to survive, we're going to do that because that's what Homo sapiens do. That's what life does. We're going to process more and more energy. Right now, we only process like 1 part in 10 to the 4th of all the solar power that the total amount of energy that humanity processes is 1/10,000th of just the solar power on the Earth, even less than that, actually.
Yeah.
So for us to, and we can't do this without choking out other life on the Earth and tremendously affecting the biosphere, the environment. And that's one of the most, that's the most precious thing that we know of in the universe. We should treat it with respect. Whereas the asteroids are rocks floating in space. And so it's a resource. So that's why even though it's only 4% of the mass of the moon, it's 4% floating in space where it's very easy to get and work with and build worlds out of and make into things without much rocket propellant required to go between places. So it's the natural resource for spacefaring civilization.
Okay.
Long answer.
Now, I can imagine you mentioned Captain Kirk, right? And just Star Trek.
By the way, I went to William Shatner's 93rd birthday the other day.
Oh, wow.
It was amazing. That guy is such an awesome dude. I mean, he's a transcendent figure in our society. He's not just an actor. But anyway, go on.
I don't know how he has that much energy. I mean, I'm 40 and I don't have as much energy as he has, I think.
Yeah, I have noticed in the last year or two, he's slowing down a little bit, but he's amazing. Just amazing.
So, the search for life, the scientific aspects of this. I mean, I can't imagine with all of this technology you're going to be developing that you're not going to get knocks on the door to do scientific missions. and potentially looking for life and things like that out there. And as we get further out, and we're using these space station gas stations on asteroids effectively to go farther and farther out, where do you see that fitting into like our future? How are we going to expand into the solar system? What does that look like? And do you think that there's potential life out there in our solar system?
So here's my answer about life in the solar system or life in the universe. And by the way, I have a very good friend who's a senior staff at Caltech. Teaches he teaches their course on exobiology, and he spends his time studying abiogenesis. And here's my scientific opinion about life in the universe. Any scientist who has an opinion is not very rigorous, because in order to have a scientific opinion, you need data, and we have no data.
Yeah, we're speculating right now.
All we have is our hypotheses. We have hypotheses about abiogenesis, how life formed from not life. And these are unproven hypotheses that in high school and college textbooks, it's taught as catechism. And it's not proven. And if we understood biogenesis, we could make it in the lab, and we can't.
Sure.
And there is no other chemical process in any of science where the instructions to the recipe are, okay, take these ingredients, put them together in a test tube, and then wait somewhere between 1,000 years and 1 billion years, and something will happen. Sorry, there's something missing there. Now, this is a grossly oversimplified discussion, but we need to start taking Fermi's paradox seriously, and we need to start thinking carefully about this. I think that the question of, is there other life in the solar system? And if there is other life in the solar system, as soon as we find it, we need to look at it and see if it shares statistics with our DNA, if it has DNA. First of all, does it have DNA?
Right.
So I had a conversation with David Baltimore, who used to be the president of Caltech, a Nobel Prize winner in biology. He said he doesn't think there's another way that you can organize complex chemicals into something as interesting as life other than DNA. That's a really interesting statement. Does it have DNA? If it does have DNA, does it come from the terrestrial tree of life, or did the terrestrial tree of life come from it? Those are really important. Or was it an independent abiogenesis? Those have profound. Then, if you had any data like that, you could have a meaningful conversation. Like, one of the things that I've done is I've won 7 NIAC fellows. I'm one of the only people that's ever won 7 NIAC fellowships. And I spent a lot of time with the NASA NIAC, NASA Innovative Advanced Concepts Group. There was a fellow named Dr. Drake, Frank Drake, who used to be on the NAC, the NIAC Advisory Committee. And he had this equation called the Drake equation. And I remember chatting with him about the Drake equation. And, my problem with the Drake equation is too many of the parameters are somewhere between 0 and 1, and we don't know anything between 0 and 1.
Right.
So it's an equation that doesn't bound anything. So anyway, so that's my thing about life. And that's why I'm really skeptical of settling Mars until we've thoroughly explored it with robotics, because we need to find out if there's life on Mars and places like Europa before we consider settling them. But I do not feel uncomfortable settling barren rocks like the moon or asteroids, because there is no credible case that there can be life there. But if there is life elsewhere in the solar system, it's the most profound and important question in science.
Okay.
Agreed.
Now, do you think, because I've heard ideas about how something like a tardigrade would be able to be living on one planet, and then something hits
100%.
that planet, and then it goes off, and then it goes and panspermia, it goes on another planet and inhabits. Do you think that's
yes, exactly?
Kind of
That's exactly the thinking behind, if there is life on Mars, we need to look at its DNA. And if it shares any common sequences in its DNA with terrestrial life, then we know that either terrestrial life came from Mars, or Mars came from terrestrial life, or they both came from some common origin through panspermia. So that's a really important thing. And there's also been suggestions that even microbes could be transported on extrasolar objects, like interstellar, comets and asteroids that get ejected and move between stars. It's not at all out of the question. I mean,
Right.
after we know what Jeff Goldblum said, and if he said it, it must be true.
Life will find a way.
That's right.
Excellent.
So
Actually,
anyway, how
that's
do I see it happening? The way that I see it happening is I see outpost on the moon.
Okay.
I see harnessing lunar resources. The beauty of the moon is that it's a resource that's close by, a few days travel, relatively low energy to get off of it. And what's beautiful about it is it doesn't have an atmosphere. Mars has a problem. It has an atmosphere that's enough to be a pain, but not enough to do you much good. On the moon, you can launch payloads off of it electromagnetically. So getting large tonnage of material in orbit from the moon could be very, very cost effective. And then the asteroids can provide all the elements on the periodic table practically. I think there's a problem with argon from the asteroids.
You mentioned like the 4% of the mass of the moon, but is that just the asteroids? I mean, if we're able, maybe I'm not really realizing the scale here, because I realize the Kuiper belt is far farther than this. But once we're out, with able to get to the asteroids, and we have the fuel from the asteroids that we're mining, which we have to get to that topic yet. We've got now a platform to go even further. So
right.
Once we have the asteroids and people are populating the asteroids, would that next step be going out to the Kuiper belt and trying to start to populate that, or is it we're bringing material back to a more habitable area?
So the thing is that life doesn't follow central planning. Life hops and grows organically. And so there might be one civilization that goes out into the cosmos that starts to build worlds. And then there's another group of people are harvesting asteroids and building settlements nearby, and they don't like each other. So one of them, you put a propulsion system on your settlement, you take your settlement out. As Buckaroo Banzai said, wherever you go, there you are. It's not a series of destinations. It's a way to live in space. And we can live in worlds that move between the planets. And we can have a civilization that spreads throughout the solar system. And some people will want to live in gravity wells. I don't know why. There's no compelling reason to live in a gravity well. If you build worlds that are big, you spin them to whatever gravity you like. You give yourself whatever atmosphere you like. You give yourself the radiation protection you like. You can tailor the environment to the species. And then with genetic engineering, you can tailor the species to the environment. Eventually, I think people will be genetically adapted to be able to live on the moon or Mars where there isn't 1G. There's no science that suggests that would be safe for humans right now. None.
Right.
In fact, there's really good science to suggest it would not. Typically, if you take any organism and take it out of the environment that it was evolved for billions of years, and try to make it live, it will have problems. All astronauts who've had long duration exposure in space have permanent medical issues.
Right.
If you notice, most astronauts wear glasses. There's a reason for that. It reshapes their eyes. Most astronauts, it also has permanent effects on the immune system and so on. Permanent effects on the skeletal muscle system. Calcium in bones is there because originally calcium was a buffer of calcium for fish swimming in fresh water. When you go into space, the calcium leaches out of your bones, and that's an irreversible process. But it's not just for the individual. These characteristics are inherited by the offspring through epigenetics. So it could be that if you live 20 years in space and give rise to children in space, those children will never be viable, or maybe not your grandchildren will be viable. And The science of epigenetics is new and we don't know. But the one place that we know that we can create truly terrestrial-like environments in space is space habitats built out of asteroids and lunar regolith.
Yeah.
And that's one of the reasons I'm a big believer in it. Now, as soon as someone shows me that you can live on the moon or Mars and that your grandchildren won't grow up and just collapse because they don't have bones, I'm open to that. But I'm also not real keen on settling Mars until we know what the situation is with life on Mars.
Will Dave make a comeback against Joel in our next round of last minute trivia? Find out after this short break.
Dive into the world of astroimaging or level up your skills with the Celestron Rowe Ackerman Schmidt Astrograph, RASA. Thanks to its patented optical design and precision engineering, RASA captures breathtaking images in minutes. Say goodbye to long exposure times and hello to instant gratification. Choose from 8-inch, 11-inch, and 36-centimeter models. To learn more, visit celestron.com/RASA.
So that actually gets us into the next thing, which is the mining, which I think is super, super cool. And so I just have a first question. This is a multiple choice trivia for you. And this is the last one, I promise.
Okay.
And I don't think you can get this wrong. So my question, you mentioned Jurassic Park, and I sacrificed my my time and I sacrificed my intelligence to watch the 1998 blockbuster movie Armageddon.
Was that the one with Bruce Willis, or was that the other one?
That's exactly the one that I watched. Yep.
Yeah.
And because I needed to do background research. So my question, and this is multiple choice, how predictive of the future of asteroid mining was that blockbuster movie Armageddon? So first option is A, solid. It's basically the same thing. B, NASA would definitely find a global killer only 18 days ahead of time. C, once NASA finds the asteroid, they would easily and quickly find fault lines and decide to drill a nuclear bomb into it, which would definitely not explode it into smaller planet killers or just get absorbed into the asteroid with no explosion. I think D, Bruce Willis has already split an asteroid in two clean pieces and saved Earth. This has been documented. Or G, Liv Tyler's acting was the least believable part.
Well, I thought the best scene in that movie was when Bruce Willis was lecturing the NASA guys about how to make a drill.
Right.
And, the engineering on it was perfect. It was perfect. In fact, we model our company on that. So, it was perfect. And,
No sarcasm there.
So, but there are some things that you said that are actually not unreasonable. So, for example, we know where the vast majority of 100-meter, kilometer-sized asteroids are that are outbound from the Earth. But for ones that spend the majority of their time between the Earth and the Sun, we don't know where they are. And we have a selection bias in our astronomy because telescopes can't see asteroids that are behind us. If the Sun is behind us, we are really good at, the Sun is behind me, so I'm looking out away from the Sun. I get really good observations. But the astronomical telescopes that we're using now to find asteroids don't even go down close to the horizon. So even asteroids that would pop up above the horizon during dusk and dawn, they're not very well seen. So, and then there's something called Manx comets. Have you ever heard of Manx comets?
No, that's a new one to me.
You know what a Manx cat is?
No.
It's a short-tailed cat, or it's a type of feline with a stub tail. I'm told. I'm no feline guy. I'm allergic.
Neither am I. I'm a dog person.
I like cats, but I'm allergic to them, so I'm a dog guy. But these are comets without tails. So comets come in much faster than asteroids because of their high V infinity, because they're coming in. And Manx comets don't have much of a tail, so you could miss them.
Mm.
And
what is the
so
reasoning for that? Is there a
it
clear
has to do
understanding?
with it has to do with the thermal history of the object and its volatile content. So
Right.
the tail of a comet is caused because as it starts to move towards the sun, the volatile materials start to boil off, and then they blow dust, and it forms a gas and plasma cloud that can be seen from Earth. But Manx comets, and by the way, every time a comet, you guys know this, every time a comet comes around through periapsis, more volatiles are blown off. So a lot of times, a comet that came by last time was very bright, and then the next time it comes by, it's not so bright, and people are like, "What happened?" The historical record is it was very bright. Well, all the volatiles got blown off last time. But there's a professor at University of Hawaii named Karen Meach who studies Manx comets, and she has convinced me that we should be worried about. We're very good at finding near-Earth asteroids, but we're not so good at finding, things that come in from the deep solar system and come swing by. Sangusta may have been such an impactor, maybe. We can't say that it wasn't. And there could be a population of fairly dangerous asteroids that are relatively close to the sun that we could see at the last minute because of the observing dynamics. And so that's one of the reasons why we want to put our asteroid prospecting telescopes out in space where they can see those objects better. So that whole 18-day warning thing, actually, there are people in the Space Force who actually think about that, and it is not universally absurd to use ICBMs as an asteroid defense mechanism. Now, I do know that there's a lot of controversy in this, and experts in the field have different opinions, and the majority opinion is that if you fracture an asteroid with a nuclear charge, it could make it much more dangerous. But it's
That's what I
not
would
universal. But it's not universal, and there are people that are looking very carefully at it. And some of those solutions that are kind of science fiction and stupid, they actually, like if you're going to innovate, you have to have your aperture open for all kinds of different ideas.
That's true.
But I mean, the way we would do it is not, I like to say that the reason we have capture bags is because the only person who can land on an asteroid is Bruce Willis. Other than that, you need to put it in a capture bag before you work on it.
That's right.
Right. You had talked about how we're, going to have the Sutter observatories on Earth. We're going to be eventually taking, this smaller telescopes, CubeSat into space. But I also saw that there's much larger plans, the Sutter Ultra even.
Yeah.
Can you just tell us a little bit about the, generational steps that you're planning in terms of space-based observation? Because I think it's pretty amazing to consider, a company that is going to be having these massive telescopes in space.
Yeah, so you start small and then you get big. Starting small is running our software on cameras that are currently in orbit. So we have a partnership with another company. I'm sure they wouldn't mind if I said, but I don't want to say who it is. It's a well-known space company that has lots of cameras in space. And we have run our moving target detection software. Midas is our total network control system, and then our optimized match filter tracking system, which operates the telescope and develops the strategy for observing and how we do the calculations for the match filter tracking. We call that module Thea, and we've actually ported Thea to run on a spacecraft operating system. And we've actually run it on a flat sat of a satellite that's currently in orbit, taking pictures all the time. And we're going to be running it on a satellite very soon. It's up there. And I don't think I'm allowed to say whose satellite it is and that sort of thing. But this was part of a activity that we actually did with DARPA recently. And so we start small, and then and then you can't see it. There's an 8-inch reflector over there, which is our mock-up, which is our ground simulator for our space telescope. The first telescope that we would fly in space that would be a dedicated built astronomical instrument for asteroids and space domain awareness, which is SDA is the acronym for finding debris in space, right? That would be about an 8-inch reflector that would have a focal plane that's a little smaller than the 63 megapixel focal planes that we have in our bigger cameras. And we fly that on a little spacecraft about that big. That's sort of step 2. And with that, we can see if there was a CubeSat flying in a weird orbit at the distance of GEO, we'd be able to see that. After that, we would fly telescopes that are very much spec'd out, like the RASA 11, but space qualified. And we'd probably want to fly 1 or 2 of those on a demonstration mission first, although that's not really necessary. Here's a weird thing to think about. You guys know what a Falcon 9 is. So the Falcon 9 bay is about 4 meters in diameter. So what's that? 13, 14 feet, something like that. So take a deck with some curvature on it. How many of those telescopes packaged for space can you fit on that deck inside the fairing of a Falcon 9? The answer is 109.
It's crazy.
Wow.
And you can package them with a moderate-sized spacecraft, and that's 1 Sutter Ultra unit. We can fly 3 Sutter Ultras, each with 109 telescopes, on a single Falcon 9.
Wow.
With
That's some good payoff.
With a single Falcon Heavy, we can fly that to deep space, and we can observe all of cislunar space and find everything down to the size of a basketball in cislunar space continuously. And when it comes to asteroid prospecting, that's the thing that starts the asteroid mining revolution. That's what leads to the gold rush to space, because we will find hundreds of asteroids, house-size asteroids in low delta V orbits every year. So that's what Sutter Ultra is. And let's think about this a little bit. We humans live on this little dust mote that we call Earth, and we're almost blind to the space around us. I'm talking about a space mission to fly at commercial cost. For the cost of one big geostationary communication satellite, we can see everything around the planet out to hundreds of kilometers, hundreds of thousands of kilometers, down to basketball size. And we can see all the targets coming at us from all directions all the time. We can be aware of all the traffic, and we can be aware of threats from planetary defense, and we can know what the natural resources in our neighborhood are. That seems to me to be a practical investment for our species that we ought to make. And we think it's important, not just for our business plans, but for the planet.
And you said this is for the same cost as a large communication satellite.
Yeah, for like a big communication satellite that they put up in GEO, those things cost upwards of $250 million. For a small, for not that much money, we can do this.
Wow. Now, you had mentioned data being an issue prior to this. You have 109 of these now.
Well, our algorithm is absolutely critical. Our algorithm is absolutely critical, because if you were to try to use brute force processing to process all that data, it would be, the solar arrays would be the size of basketball courts. But actually, when you run the numbers, it's very reasonable. Few kilowatts can do all the processing. And you don't have to send all these images down. By the way, the terabytes of data that you generate, you can't downlink all that data from space. Even with optical comm, it would be a heavy load. But you can download the tracklets and the ephemeris, what we call TLEs of the targets, and then when people want specific images of specific things, we could send that down.
Right. Now, if I remember correctly, you were showing this in one of the videos about how the 3 Sutter Ultra telescopes or more could be kind of aimed at different directions, like towards Earth, towards the moon in one of them, and then kind of at just different angles. I could probably include some of that in this podcast.
We have two animations. I hope we can get them both to you. One of them is, what if you wanted to use Sutter Ultra to monitor everything that's happening in cislunar space? In which case, you could put 3 telescopes at, I think it was L4, L5, and L2. It was definitely L4 and L5. I think the other one was L2, but it might have been L3. No one ever goes to L3. But the animation shows it. And with that, you can monitor, you can see everything moving in cislunar space. And the animation shows that, if at the worst possible time there's a launch, you're still going to see it.
Right.
But then you put the same telescopes in a what we call a pseudo-retrograde heliocentric orbit. It's an orbit that seems to be an orbit around the Earth, but it's not. It's actually a heliocentric orbit with a semi-major axis of 1 AU. So it has the same period as the Earth's orbit around the sun, but it's got some eccentricity on it. And what happens is, if you position the spacecraft correctly in that elliptical orbit around the sun, it actually circles the Earth as it goes around the sun, but it's not gravitationally bound to the Earth. It's outside the heliosphere. And if you do 3 of those, you're going to have them circling the Earth at all times. There's always one between the Earth and the sun, looking out past the Earth for planetary defense targets, or what we call missions of opportunity for asteroid mining. And the way we see asteroid mining working in the future is we have this observation system that's constantly watching for inbound asteroids. And when a new asteroid mining target comes up, we know statistically they're going to come up with some frequency, and there's a random distribution of when they arrive. But we know every N months one will be coming up. We pre-position our asteroid mining vehicles at the edge of the Earth's gravity well. When they come up, as they approach, we chase them down, mine them, and then the next loop around the sun, we come and return the resources to the Earth using a lunar gravity assist for capture.
How much of the material do you think would be returned to Earth versus keeping it
depends.
out in space?
It depends. Early on, we think the most valuable resources will be volatiles. Hydrogen, oxygen, carbon in the form of carbon monoxide, carbon dioxide, methane, and those are used to make rocket propellant. So early on, we harvest these things for rocket propellant. So the way that we put it is, our first generation full-scale asteroid mining vehicle weighs about as much as a consumer pickup truck, a big consumer pickup truck, which is about as much as a big geostationary communication satellite. And it has inflatable solar reflectors that are each like the size of a tennis court. And it's launched on a normal Falcon 9 class rocket. And it flies out to an asteroid that's one of these low delta V targets. It captures it in a bag. The bag weighs about 1,000 pounds, and it can capture up to a 1,000-ton asteroid. You say, 1,000 ton, that's a really big number. That's an asteroid about as big as a big house.
Okay.
And it captures it in a bag, and it can extract mostly water, about 100 tons. So that's about as much water as goes in a backyard swimming pool. And it brings it back to geostationary orbit, where we can sell it. We actually have a contract with a publicly traded company to sell them 100 tons of water in geostationary orbit for rocket propellant. That's worth about $750 million. And so the way to think about it is, early first generation asteroid mining, spacecraft weighs about as much as a big pickup truck. Inflatable objects on the spacecraft deployed to the size of tennis courts, captures an asteroid the size of a house, brings back amount of water, which is roughly a small backyard swimming pool. That water can be held frozen in a flexible membrane enclosure that's several meters in diameter. And that's worth the better part of $1 billion just for water.
Wow.
Now, once we have plentiful supplies of rocket propellant and our omnivore propulsion system working in space, our worker bee orbit transfer vehicles, take a worker bee orbit transfer vehicle, add the mining equipment to it, you have a honeybee. Once the honeybees are operating off of water supplied from asteroids, it starts very quickly to be as cheap as air travel to get around in space. At that point, and only at that point, after the transportation revolution has taken place, then it makes sense to go after precious metals to return to Earth. But on the basis of today's markets for precious metals and today's costs and today's transportation systems, it makes no sense.
Okay, so we still have a lot of steps to go before really getting into mining asteroids, right?
No, I think the water harvesting, we put the four technologies together.
Okay.
Detect, move, capture, and process. Each of those have commercial applications in low Earth orbit and other places. You put those four things together and you're harvesting water very quickly.
Yeah. Now, there are multiple fuels being used even now with respect to rocket propellant. There's kerosene, there's methane, there's various, more exotic things. And then there's hydrogen and oxygen, right? The same thing that the Apollo program basically was run on. Looking at that and what you'd expect to see from these asteroids in terms of the volatiles, is there something that maybe is the diversity good, or is the diversity in different types of rocket propellant an issue that maybe should be considered?
I mean, that's kind of like saying, we have all genres of movies. We have science fiction, we have drama, we have romance. Is the diversity good or bad? The diversity is generated by the market, and the market is the most efficient system for deciding.
Right.
Now, if I was developing a rocket, I would use LOX methane for the first stage and LOX hydrogen for the second stage. That's what Stoke is doing. That's what Blue Origin is doing. SpaceX is using LOX methane for both stages because they want to refuel at Mars where they have carbon. We can sell water to LOX hydrogen or methane from asteroid resources. Lunar resources really pin you down to LOX hydrogen. But I think LOX hydrogen is the chemical rocket propellant that will drive humans around. Our omnivore thruster can operate either as a chemical rocket on LOX hydrogen or as a hydrogen rocket with a specific impulse of 875 seconds when it gets energy from the sun. So I personally believe in LOX hydrogen, but that's like, do you like science fiction better or rom-coms?
Right.
I think there's room in the market for everything. I love LOX methane. The one thing that is going to die is kerosene.
And just for clarification, the LOX is the liquid hydrogen, liquid oxygen that we're using for the rocket propellant. Liquid oxygen is LOX.
Yeah. Sorry, not LOX and bagels. LOX and hydrogen. Yeah, liquid oxygen, liquid hydrogen.
This is the transcontinental railroad to space, right? The same type of journey that we saw as people migrated west in the United States. We're basically doing that into space. Do you see yourself more as an explorer, or is it just your scientific curiosity that drives you? How did you get here? What was the internal motivation that for you that made this possible?
There's two kinds of people. People who organize people into two kinds of people and everyone else. Sorry. One way to distinguish between different groups of people is there's some people who, like, when you drive on the freeway system in LA, there's always mountaintops in view. And I like running on trails. And I always look up on the mountaintops and I ask myself, I wonder if anyone's ever run to that mountaintop. And then when you ever run to a mountaintop that has no human trails on it, you get to the top of the mountain and there is something somewhat indescribable about the moment.
Yeah.
And to me, this is just an obvious thing that any human being would feel. And I mention this to people, like I'll be driving down the street. I go, wow, I'd like to go to the top of that hill. And I've had people go, why would you do that?
Oh, bummers.
But I mean, but historically, Homo sapien, I think, is adapted so that most people are in the. If there's not a reason to go up to the top of that hill, I'm not going to go up to the top of that hill. And then there are some human beings, there are some Homo sapiens that have this thing where if you were a Paleolithic hunter-gatherer living in a valley and there was a mountain, you'd have to go find out what's on the other side of the mountain. And that's one of the superpowers that we Homo sapiens have, is that we have both kinds of people. Majority of people want to stay in the valley, and a few people want to go to the top of the mountain. Now, I happen to be that kind of a person. I'm not an explorer, I'm an engineer and an entrepreneur, but I feel that wanderlust in my heart. And when I look to the skies, they call to me. The stars, as Carl Sagan says, the stars call to us.
Yeah.
And what was it? He said, the stars call to us, and if they do not destroy us, we will someday venture to the stars. And it's because there is a subpopulation of Homo sapiens that must see around the corner. Those are the ones that will build the settlements. And those ones who build those settlements will have a higher percentage of those genes in their population. And they will build more, and they will spread further. And in 100 years or 1,000 years, they will spread throughout the solar system, and there will be 100 billion of us. And by that time, the nuclear technology to take those worlds and send them hurtling between the solar systems, to send them hurling between the stars in our galaxy, will be trivial. And the fact that you already live in space in this settlement means I don't care if I'm in orbit around Earth, Mars, Saturn, or if I'm hurtling between the stars. It's the same. I'm Homo sapiens cosmos. I'm a citizen of the universe. And so the idea that, people couldn't do long travel between the stars, no, we have the basic science to do it now. We just need to develop the technology, and it's relatively easy relative to what we have now. Once we're building worlds made of asteroids, we'll be pushing them around the solar system. And some people will go, it's too crowded here. Why don't we get 30,000 of our best buddies and head out that way, and our grandkids will be building worlds on Sirius, which we know has an extensive asteroid belt.
I mean, dreaming toward the future. This is it's interesting to see how different people have different visions of the future.
It's really the same vision that drives Elon and Jeff drives most of the entrepreneurs that are driving new space. Elon sees people living on planets. Isaac Asimov said that was planetary chauvinism. It's a form of chauvinism where people have always lived on planets, so let's do it in the future.
Right.
This is where Elon is probably the best spokesman on the planet for not thinking by analogy to the past and thinking in first principles. And he just doesn't think in terms of first principles when it comes to where humanity will live in space. It's obviously not at the bottom of gravity wells. They'll visit those on expensive vacations. But
one of the things that Jeff Bezos did say that really caught my attention, and it means a lot to me, is, one of my personal goals is to see all of the national parks. And we have a travel trailer. We go around and want to show our kids the country. And he said that he foresees that all heavy industry is being done in space, and that Earth is a national.
Yes. And that should be true of any planet with a biosphere, any planet that has indigenous life. Unless the indigenous life is really, just in one little place, then you can put a dome on it and terraform the rest of the planet. Heck, we might find out that life is just so plentiful in the universe, it's no big deal. And, as Bob Zubrin says, who cares about some microbes on Mars? That may be the thing, but we don't know that yet.
Right.
But, the point is that TransAstra is a company where we have this stuff in the back of our mind. We don't talk about it all the time. We talk about writing code and debugging software and figuring out why the RF system on the mass simulator for our capture bag isn't connecting. And we talk about getting more performance out of the algorithm on our Sutter telescopes. We are very practical engineers and business people, solving real world problems, driving revenue growth every day. But we are not just, the reason that this vision is important is that people need to understand that there's more to life than lunch, and that it's about having an infinite future for our species, an infinite positive future, that there is tremendous reason for optimism. By the way, if you're not optimistic, you're not going to be very productive. And so we have a right to be here. We have a right to enjoy our lives, and we have a responsibility to make life better for our children and for the other people of the world. And that's part of being a productive and practical engineer and business person.
Agreed.
In saying that, it gets me thinking, we have a group of our listeners, I'm sure, who are interested and inspired and young. And, they're listening to this beautiful future that they're wanting to help make happen. What are some of the things, skill sets that you need as you scale this to do the work that we've been discussing? What kind of skill sets are these, young people needing to come into the industry to help to make this vision possible?
Everything. There's no skill set that we don't need. If you're talented in mathematics and spatial reasoning, then you should go into STEM. And when you go into STEM, don't limit yourself to what you learn in school. The best engineers are born, they're not taught in schools. One thing that we notice in our recruiting is there are a lot of candidates who we pass by who are very book smart and they got great resumes and they got great grades and they're very talented. But you go to have them design a table and they don't put gussets in the table to keep it from going like this, because they have no common sense, because they didn't build model airplanes and drones and model boats. And we need people who are very smart and theoretical, but they think with their hands and they build and they write code. Like if I talk to a computer software developer who's graduating in computer science and I say, well, what languages do you know? Oh, C++ and Python. Well, what about Java and Rust? And how are you on SQL? Well, that wasn't in the curriculum. Well, you mean you only learned the languages that they taught you in school? You're not a computer scientist. You're a student.
Right.
I have, but you talk to a kid and he goes, yeah, which languages do you know? And he starts listing them off and he runs out of the language, the fingers on his hand. And how long does it take to learn a new language? Well, I can learn a new language in about 3 days. I mean, it depends on the language, I taught myself Rust last week, but Rust is a derivative of C for embedded systems. And I've been building embedded systems on Arduinos since I was in 7th grade. Okay. I'm going to hire that kid.
Mm-hmm.
So it's about whatever. So if you're in STEM, that's the attitude. If you're an artist, show me your art. And if an artist comes and you're doing a Zoom meeting with the artist and there aren't a whole bunch of artworks behind them, they're probably not much of an artist.
So are you kind of saying get your hands dirty? Don't just follow the curriculum and do exactly what they give you. Get your hands dirty and do some extra engineering and work with your own stuff, throw your own pots, do your art and get messy with it. Is that's
exactly right. Life is a contact sport. You need to burr your knuckles from turning wrenches, figuratively and literally. And building is a team sport. And if you can't get along with people, you can't be a very good builder. So what have you done with others? I had a wonderful experience. So if you go to the TransAstra website, www.transastra.com, and click, I think it's on the tab over on the right is like media, and go down to videos. The top video there is a video about me and our company that was made by a graduate student who's doing media and an MBA at USC. And they had a film festival the other day where they invited me and the other people that they made videos of. By the way, that's an example of a kid who makes videos. Like take a look at that video and see what an awesome video that is. Like
Right.
if I was a movie producer, I would hire that kid in a second. That's like better than half the documentaries you see on the History Channel. But what was really cool is that there was a bunch of kids who were interested in entrepreneurship who showed up. My panel went on at 8 p.m. last Thursday night. And I walk into this auditorium in some nondescript building at USC, and I see all these very positive kids just leaning forward. Almost all of them were like, they were dynamic and healthy and enthusiastic. And like when I got done, they'd seen that documentary. That's a little 15-minute video that this kid made, which is outstanding. I hope people check it out. And then we had this panel discussion with some other founders, and they were like raising their hands, and like afterwards they were mobbing me with those kinds of questions, asking, what do I do? How do I get into this? And that sort of thing. As soon as they hear about the prospects of a positive future for humanity and their ability to contribute, they go on fire. And you can't believe.
Solutions based instead of just recircling.
100%. And, like young people want to contribute. They want to have meaning in their life, and they want to have a future. And, and when they do that, they find other young people to love, and they have kids, and they build families, and society thrives.
Yeah.
And that we need more positivity that causes society to thrive and grow.
Yeah, I noticed in your videos, you definitely have a younger workforce, at least from what I could see from the videos. And
yeah, I think the most common age, probably the median age in the company is probably 24, 25. Okay. Now, the company has some senior people in the company. So we have a MIT PhD in laser physics, and who's got 25 patents in radars and electronics, who's our director of innovation. We have Dr. Hayden Burgoyne, who's mid-30s, PhD, 2016, Caltech. We have, recently we hired Dr. Thibaut Talon, Caltech PhD, a few years after Hayden. Amazing mechatronic engineer, knows every discipline of engineering, just an amazing guy. We have my brother Patrick, who is a brilliant journeyman engineer who knows people think the word journeyman is the wrong word. He's a master engineer of several disciplines. And so we have a mixture of youth and enthusiasm and energy and talent and experience. And we have people who've suffered the hard knocks of life and the thrills of success and victory. And we have people who are hungry to do all of the above. And it's just wonderful watching it all work together.
Yeah, I was going to ask if you, as we're rounding this out a bit, and you're looking at your company, I was going to ask if you have like any particular guiding principle or motto, because I heard one that I thought would be a good one in your video, and that was nothing's a bad idea until you prove it's not viable. And I thought that was pretty good.
I like
but other
that.
than that, like, do you have other like is there something that you hear around the hive all the time, or a certain kind of motto that you have for the company?
We don't have a catchphrase. Engineering the future of space is the closest thing we have to a catchphrase.
Mm-hmm.
But there are certain values that we hold very dear and that we make sure are communicated. So they're basically courage, joy, work, and integrity. So courage is you must be willing to fail, as painful as that is, and you need to take chances.
That's hard to teach.
Work is If there's a job that needs to be done, you focus on it. And if you're late, you get it done. And integrity is you tell the truth. Also, part of courage is you need to be disagreeable. So there's a parameter in psychometrics called agreeability or disagreeability. And we find that it's very important for engineers to be disagreeable, to speak up when something doesn't work. Integrity is at the core of the success of the human experience, is the integrity that came from the Enlightenment and the scientific method. The concept of a shared objective reality that is concrete and believable, that we all trust in, and the fact that when someone opens their mouth to speak, you can trust that what they're saying is true. You cannot engineer and you cannot have teamwork without it. So it's those four things.
I like
those are the guiding principles of how I try to live my life. I fail miserably at it.
Well,
but
we're human,
try.
right? I mean,
right, and that's okay.
Yeah.
It's not how well you do relative to perfection. It's how well you're doing relative to if you weren't doing your best.
Right.
And how well you're doing relative to last week.
Joel, what do you think about AI and what kind of impact it's going to have on this industry?
There are a lot of people confidently saying that's a huge revolution, and it might be. And if it is, the magnitude of the change almost is beyond imagination. So I do believe it's quite feasible to build humanoid robots that are right out of science fiction. Sell them for $10,000 a copy and have them do things like mow the grass, assemble that 80-20 structure over there. And then AI is going to enable us to build giant factories in space that consume asteroids and turn them into worlds faster than people think. It's stunning what may come. Now, there also may be a brick wall that we hit, but I think it's going to work. And, we use, obviously, like any other tech company, we use AI in everything we do every day. It's just in the water. And it increases our productivity, and it works, and it's very helpful. I made the mistake of saying we use it to help write proposals. Someone quoted me as saying, TransAstra uses AI to write its proposals. No. You can't trust it.
Right, you
what
iterate
we do
off of it.
is we use it to, it can increase your productivity in writing, but it still has to be written by a human. Same thing with software. And, and the smart young engineers have figured out, and smart old engineers too, figured out that get stuck on a problem, go ask your favorite large language model. They are amazing. And and here's what I tell the young engineers. They're amazing. They can get you out of all kinds of blocks, and they are literally always wrong. Once you get anything of any depth, they will eventually start spouting pure AI-driven BS. And they can't help you do something that you don't understand the physics on.
Right.
No, well, at the best, they're as good as the information you provide it, but they always make conceptual errors and mistakes. It's just whether they rise. And every time I've ever gotten into something deep with the AI, eventually it started to spout gibberish. So, but it's fascinating to watch. Human beings learn about 1 million times faster than large language models. And there are structural reasons with that large language models are so inefficient. It takes 1 million times as much training. I think that's a solvable problem. And once that problem gets solved, like right now, the AI industry is consuming massive quantities of power. There's a software problem in the way they're organized that they need to get more efficient. If they get 10,000 times more efficient, which seems completely reasonable, that power problem with AI will go away. Yeah. So that's something I'm watching. That's interesting. And the executables of the models are very power efficient. Probably next year we'll have nice AIs built into, phones. God, I hope they're better than Siri.
So Joel, I want to just mention something that we're putting together a Cosmos Safari podcast merch, line where we have T-shirts and mugs, and I'd like to send those over to you as a thank you for being on tonight. And they're available for everybody. If you're interested, you can now get them on Celestron's website under their merch. So I would love to send those your way, and thank you so much for coming on tonight and providing us with your time. Please, if there's anything that you see coming that's of something that you'd like to talk more about, we'd love to have you back on. It was such a great time to talk with you tonight.
Well, awesome. I had a ball. Thank you guys so much. This was fun.
Yeah, this was fantastic. Thank you so much for taking your time with us. Appreciate it.
Peace.
If you're still listening and like this podcast, please consider becoming one of our Patreon patrons. Memberships start as low as $3 per month, with benefits including opportunities to ask questions of our guests. Also, please consider liking, subscribing, and sharing this podcast to help us bring the universe even closer than you think. The podcast will be available every third Tuesday of the month.